Welcome back, everyone. So today we were going to do some applications on the relative motions of rigid body, and we started this topic last time. So here, lecture number 5, relative motion, and we will be doing some application on acceleration. So for this, last time we have our velocity v at b is equal to v at a plus vb with respect to a. And we did the same for the acceleration. We got vb equal to a plus ab with respect to a. And we said that this will be equal to a plus the tangent component of ab with respect to a, which will be alpha pa crossed by RB with respect to A, and the normal component, which will be omega BA square multiplied by RB with respect to A. And this is the acceleration at B. So we have tangent and normal component. And this is the equations for no slipping. No slipping. So let's solve an application on these equations. So last time we started to solve the system of multi-bar linkage, and we solved it for velocity only. We didn't solve for acceleration. And we were able, knowing the omega of CB, we were able to get the velocity at B, and then we used the velocity at B to get the omega of the body AB, and by getting the instantaneous center of zero velocity. And then we were able to get the velocity at A, and then we were able to get the omega of OA. And then this is the omega of AB, and this is the omega of OA based on the last lecture. So what if I told you that the alpha CB is equal to 0? How about the alpha of the body AB and the alpha of the body OA? How can we get them? So let's construct this equation again and put the acceleration equation to solve this problem. So here's OA, and then A, O, B, and then we have C here, and you are given the omega of this one, omega CB, is equal to 2 radian per second, and the alpha CB is equal to 0. So what about the alpha of AB and the alpha of OA? And also you are given the dimensions, and this is 0.05 meter, 0.05 meter, have this 0.075 meter, 0.175 meter. So you are given these dimensions, and let us solve for the acceleration. So for the acceleration, we need to construct the equation. So if we want to solve for the acceleration at point A, for example, okay, so let's write here, example, part 2, acceleration. For example, if we want to construct the acceleration at A, it will be equal to the acceleration at B plus the acceleration of A with respect to B, if I want to construct the acceleration at this point. And actually, if I want to get the acceleration of point P, the tangent acceleration will be equal to 0 because alpha CB is equal to 0, but we will have a normal acceleration in this way. Similarly, the acceleration of A will base on the omega. So we got omega OA based on our solution of the velocity. So if we want to solve for the acceleration, we need to have all the omegas from our previous velocity analysis problem. So your steps is to solve the velocity for the velocity verse to get the omegas, and then you move forward with the omegas to get the acceleration. So based on the omega OA, so you can get here, this is the velocity direction, and we can assume that the alpha of this body, so we need to do some assumptions. This is the omega OA, and this is the omega AB. It's in this direction. So what if we make an assumption that the omega AB is in opposite direction, sorry, alpha AB is in opposite direction, and the alpha OA is in opposite direction like this. We need to make an assumptions for the omegas, and if it gets negative, that means it's in opposite direction. So why we need to do this? So we can start with something to build this equation. Because if we want to get the acceleration at A, so we will need to have A at A tangent plus A at A normal will be equal to A at B tangent plus A at B normal plus AB tangent plus EA with respect to B normal. So this is our equation. So let's get the AA tangent. So based on AA tangent will be equal to alpha OA crossed by RA with respect to O. And it should be something in this direction. So this will be A tangent plus, and let's make it negative omega OA squared crossed by, not crossed because we will use this, the one that has R A with respect to O vector. It will be crossed if you put it in this form. This crossed by omega OA crossed by RA with respect to O. So you can put it in this form and it has positive, or you can have it negative omega OA square RA with respect to O. So we will be using this form now. And I'm pretty sure based on this, so we will have A normal in this direction. And this should be equal to AP tangent, and this should be equal to, if I want to get the absolute acceleration of B, it will be something like this, alpha CB vector. I will get the acceleration of B from C because C is not moving, and this will be multiplied by RB with respect to C minus omega CB squared crossed by RB with respect to C. So I got the tangent and normal components of P. So let's move to A with respect to B tangent. This should be, so we are moving to the body AB, and we need A with respect to B. So let's put this so the tangent will be equal to 0, AB tangent, because alpha is equal to 0. And we will have A P normal. So what about A with respect to B? A with respect to B, it will depends on the alpha. So alpha A is counterclockwise, and you will have something, so let's A, and we will have B. And if I draw perpendicular like this, and I know that alpha is in this direction, alpha AB, so this will be AA with respect to B tangent, and I'll have AA with respect to B normal is in this direction. Okay, so let's write them. So this will be alpha AB crossed by RA with respect to B minus omega AB squared RA with respect to B. So I put all the components. So let's see what I have and what I don't have. All right, so for this equation, I need all the R's. So I need this R, and I need this R, and I need this R. So let's get this R. So we can have RA with respect to O. So this and this point, I know that the distance from O to A is 0.1 meter, and it's in the positive because if I draw a vector, it will be something like this. It's in the positive J hat. So it has 0 in the I hat direction plus 0.1 in the J hat direction. So this is RA with respect to O. Then we will move to RB with respect to C. Okay, is that R? What is this? I think, yeah, RB with respect to C. So we need this vector, RB with respect to C, and it's all in the I hat, and the magnitude is in the negative I hat, and then the magnitude is 0.075. So it's a negative 0.075 in the I hat direction plus 0 in the J hat, because this is how the vector look like. But for vector RA with respect to B, which is this vector, it has a component in the X direction and component in the Y direction. The X direction magnitude is 0.175 and the Y component is 0.05. So it has negative 0.175 in the I hat plus 0.05 in the J hat. So I got all the R XY components. How about omegas? We have omega OA here. We got it from previous problem. So omega OA vector is equal to negative 0.43 because it's in the negative K hat, negative 0.43 in the K hat direction. And omega AB is also in the negative K hat 0.875. 0.857, sorry. All right, so OA, omega CB, and we already given the omega of CB equal 2 radian per second, and it's in the positive K hat, 2 in the K hat direction. So right now I can solve this equation. I have everything. So let's with the equation. So alpha OA, so let's move back here and actually let's draw a more clean version of this problem. So right now this is the directions. I have this is O, A, B, C, and I have alpha omega CB is equal to 2 radian per second. And the alpha CB is equal to 0. And I have the omega AB is in this direction. And the alpha AB is in this direction. And omega OA is in this direction, and alpha OA is in this direction. So this is the directions that we have. And let's put them in the equation. So alpha OA, we can write it as, so let's substitute alpha OA as a magnitude, and it has a direction in the K hat from the right hand rule. And let's cross this with RA with respect to O, which is this vector 0 in the I hat direction. So, and only 0.1 in the J hat direction. So this is verse 1. Then minus omega OA square, which is, we only need the magnitude, so it will be 0.43 square, multiplied by RAO, so it will be 0.1 in the J hat direction. This should be equal to alpha CB. Alpha CB actually it's equal to 0 because It's already given here. So this term will be equal to 0, alpha CB. And minus omega CB minus omega CB is 2 and should be squared multiplied by RB with respect to A. Oh, this should be RB with respect to C, sorry. So RB with respect to C, and this is negative 0.075 in the I hat direction. So I'm done with this one. Let's move to the next one. This should be plus alpha AB, and alpha AB is in the K hat direction, so it will be K hat crossed this one, crossed by RA with respect to P, which is this vector. Hat, and the next term is negative omega AB squared, so it will be 0.857 squared multiplied by RA with respect to P. In the I hat plus 0.05 in the J hat. All right, so in this equation, the only unknowns that we have here is the alpha OA and the alpha AB, and we have, this is not only one equation, this is two equations, because we can separate X direction from the Y direction. X direction is the I hat, the Y direction is the J hat. So we can separate the terms that have J hat and from the terms that has an I hat. And after actually we do these multiplications. When we are done with these equations, we will get the equation in the I hat. Like when you multiply, this will be equal to 0.1 alpha OA, and you multiply K by J, so you have K and J, and multiply them. This should give you negative I hat. So this will be negative, and this will be in the I hat direction. And do the same with everything here, but make sure this is a cross product, this is a dot product, this is cross product, so you should be able to differentiate between how can you conduct each one of these products. And finally, you would get this equations, negative 100 multiplied by alpha OA will be equal to plus 300 minus 50 alpha AB plus 128.5, and the one in the J hat direction, it will be negative 18.32, and this equal 175 alpha AB minus 36.72. From this equation, you can get alpha AB, and alpha AB will be equal negative 0.105 radian per second, which means that the assumed direction is wrong and it should be in opposite direction. And then substitute in the second equation to get alpha OA, so negative 4.29 radian per second square, because this is alpha. And this is how we solve the problems. We will not be able to do this like what we did in the, to use the scalar form, because it will be very difficult, because we have many vectors with many cross products. So we will have to solve it in a vector form. Like you will have to construct this equation and then identify the length of each vector and the magnitude of each vector, and do some scalar dot product and cross product. And finally, you separate the X direction from the Y direction to get two equations to solve for the two unknowns that you have in this problem. And this problem is acceleration without slipping. So let's see what if there is a slipping. So let's continue. Motion with slipping. So for motion with slipping, as we write the equation last time, we will have the VFB will be equal to VA plus VB with respect to A plus VB with respect to P. And we called this is the slipping term. And this is something like what we see from the last time. You have and this is pinned at this location, and you have a collar here, and this collar is attached to something here that is rotate, and this is point A, and this collar point A. So the point on the bar A, and let's call it bar AC, if we take this bar out here, the point here is B, and there is a collar on the top of this point. It's called B, this collar. And first, you will have VB will be equal to the velocity at A, and velocity at A here is 0, but you have B with respect to A. So if we have point A up here, and this is point B, and you know that the omega of this body like is moving this way, so this will be VB with respect to A. So you got this one. And B and A should be on the same body. For B with respect to P, so as soon as this body will move this way, the other body will be moving this way, and point and this color B will go down at some location here. So we'll have B here and B here. So when we say VB with respect to P, it will be something like this in this direction. So this is B and P are on different bodies. Okay, so this is for the velocity. If we want to write the same thing for the acceleration, so we'll have AB equal to AA plus AB with respect to A plus AB with respect to B. And this is the slipping term. But for the acceleration, it's much more complicated because each one of these has a tangent and normal component. Tangent and normal, tangent and normal. And this one has 3 components. It has a tangent, it has a normal, and it has another third component, which I call it as Coriolis acceleration. And this is equal to the omega of the body AB crossed by VB with respect to B. So this is the third component, and you will find the proof in the Hepler textbook for this relationship. And if we want to expand this equation, so it will be something like AB in the tangent plus AB in the normal will be equal AA tangent plus AA normal, plus here we will have AB with respect to A tangent plus AB with respect to A normal in another 3 terms. So we'll have AB with respect to P tangent and another component normal and another third component, which is the 2 omega B, and it's a vector crossed by VB with respect to B. So this is the longest equation that we have in this course. This equation to solve for the acceleration with slipping. All right, so let's see the, I showed you guys some of the applications on the slipping. So let's solve another equation, so let's see a couple of applications so we can remember how we map the velocity vector and the acceleration vector. So for this, let's have body like this, and we have a small groove here. Something like that. And we have a body that intersects here. At this location, and there's like a bend that allows this body to move on the other body. So we have this point O, and this point is P, and this point is A. And we get this body is moving with omega OP. Actually, this will be omega OP in this direction. And this body, let's call this C. If this body is moving this way, this body will be moving this way with omega AC. So if we want to know which one is sliving on which one, so you will have this you will have the groove here, and this is the point on this body, and let's call this P, and you have the other body that intersects on this one, something like that, and it will has the point P. So if we want to construct this, so the B is on this body, so you will have something like and this is point B on the left body, and this is point A, and you can get the velocity of B with respect to A, it will be something like that, VB with respect to A, if you have the omega is in this direction. And actually, if you have the omega in the opposite direction, something like that, omega AC, so this will be in the other direction like that. So VB with respect to A, based on this omega. And if we want to the velocity of B with respect to B, like if we want to know, so what we do if we want this term, VB with respect to B. So let's see. So we have B here in this body, and we have B here in this body. So, but the point P, this one, is only allowed to move in this groove. So you will have B here, and at some point, after some rotations, this arm will be something here. So B will be in this way, and you have B here and B here. So you will have a direction like that. So you will have V B with respect to B is in this direction. However, based on this omega, you will have VB with respect to A is in this direction. And VA is equal to 0. So now you have all the terms VA equal, sorry, VB equal to VA plus VB with respect to A plus VB with respect to B. So VA is equal to 0, this one. VB with respect to A is in this direction, because you have the groove is here, and this is point P, and the other point is moving in this way. So you know the direction of this velocity, and VB with respect this one, we got it, so you can get VB. Also, let's see another example on how we can map the velocities. And you should train yourself very well on doing this type of problems, because you will be asked in the next quiz on how to map the velocities. So we have this two bars. Its bend has a fixed axis rotation here. This is point O, this is point A, this is point C. And you got an omega of this one is moving, omega OA is moving this way, and actually this body is making another omega with respect to the other body. So this is omega of AC with respect to OA. First, you will need to identify the omega of the body AC. And as I told you from the last time, so you have an additive motion. So the omega of AC will be equal to the omega of OA plus the omega of AC with respect to OA. So you will have to add them, this two omega. And from here, omega OA is in the negative k hat direction, and the other one is in the positive k hat direction. So they will be subtracted from each other. So what if we have a color here? And we have point B on this color. So what we do, as I taught you, we have here, and there's a point P, blue this color, and we have the color B on the top like this. Okay, so we construct our equation based on point A. So we have point A here. So let's make it black. So as we have B and A are the same body. So we will look at point A. And for point A, we will have VA will be equal to, sorry, we will need VB, not VA. So VB, the velocity of this color, will be equal to the velocity of A at this point, and we actually can get it from this omega by multiplying the omega of R, and this is perpendicular, plus VB with respect to A, plus VB with respect to B. And if you want to make sure that you make it right, B over A, cancel, B will be equal to B, so I did this equation right. So let's map the velocities. So we mapped the VA, and VB with respect to A, so here's A and there's B, and we have we will need the omega of AC. We can get it from this equation to know the total omega and know the direction. So if the final direction was in this way, omega AC, we will have VB with respect to A in this direction. So we got this one and got this one. What about VB with respect to P? So let's assume that this color slipped down there, here. So this is point P, came here. So we will have VB with respect to B in this direction. So this will be VB with respect to B is in this direction. So we got the direction of VB with respect to B, and now we are good to go to solve this problem. So this is just some applications you will be given in the next exam, a different problem to map the accelerations and the velocity on the problem. Okay, so let's now solve an example with numbers. So let's example. So for this example, we have a ring like this. And this ring is attached here to a fixed location, middle, and there is a bar that is pinned here. And there is a double collar at this location. So there is a collar on the ring like this, and there is a collar on this body like this. Okay, so this, let's call this as point A, and this is point B, and this is point C. And let's construct our equation. So what we have now this bar is getting an omega equal to 3 radian per second in this direction. And at this location, we can identify that the theta, because this is R and this is R, so this will be 45 degrees. So what we have here, we have this arm like this that has a color like that, and this is B, and it's moving on that in this path that is fixed, but actually it's changing its direction, like keep it changing its direction like this, and we have the point P on this path like this. So B and A should be like the A, I mean like the A here is the one on the ring, A like this. Okay, so let's construct our equation with the velocity. So the velocity of the color B will be equal to the velocity at A plus maybe at some point I give you a problem that this is not fixed and this is hinged and this ring is rotating about this hinge. So it will be, we will have VA, but based on what you are given in this problem, and I told you that this point is fixed, so VA will be equal to 0. Okay, let's build the equation. VB with respect to A, VB with respect to B. Okay, so VA will be equal to 0 because this point is not moving, and VB with respect to A, so we will need the VB with respect to A, so it will be the omega. Okay, let's actually, I think it will be more easier if we solve it in a different way. So what if we considered that point B on this bar and point C is on the ring, and knowing this, so we will be able to have an R like that, and knowing that this bar is moving with this omega and rotating about this, and the omega is equal to 3 radian per second, I will be able to get VB with respect to A. So, and VB with respect to B, this one. So if you move this bar and this color B get down like this bar, let's assume that this color is part of this bar, and this color is moving at some point here, so it's leaving point P. So you will find, like, if I have, this is the curve, and this is point P, and I have my bar like this, and I put B is here. So, and you construct a vector, so you will know VB with respect to P. It's in this direction. Or it could be in the other direction. So you will have to do some assumption, and if it's in the other direction, so the our assumption is wrong. Okay, so let's solve this problem. From first, and given that this is a circle, you know that this VB is tangent to the base. So we know the direction of VB, but we don't know the magnitude. So we can have VB is in the negative I hat. Let's make it in blue. And this should be equal to 0 plus VB with respect to A. And actually we can get this by multiplying cross product of omega, and this is RB with respect to A, and this VB with respect to A. So this will be omega crossed by RB with respect to A. And let's move to the third one, VB with respect to B. And this should be in magnitude like this, and we know the direction. So we know it's going in this direction. And actually, 1 unit of this direction has an angle 45 degree. So we know the I hat and the J hat of the 1. So if we have a unit of 1, it has cosine 45 in the I hat and sine 45 in the J hat, 1 and 1. So the direction will be 1 cosine 45 in the I hat plus 1 sine 45 in the J hat. So this is for the direction of VB. Okay, we know omega, and we know the RB with respect to A here. We know this vector because it's given in this problem that R is equal to 0.4 meter. And omega is in the k hat direction, so we will be having negative B in the I hat equals 0 plus omega. It's a 3 in the k hat direction crossed by 0.4. The R, something like that. So this is RB with respect to A. It has 0.4 in this direction and 0.4 in this direction. So 0.4 in the I hat plus 0.4 in the J hat. And VB with respect to B, cosine 45 in the I hat plus sine 45 in the J hat. And here in this problem, we will have negative VB, and you multiply K by I, it should give you 1.2 in the J hat, and K by J should give you negative 1.2 in the I hat, and plus VCB cosine 45 in the I hat plus sine 45 in the J hat. And in this equation, you can divide it into two, one in the X direction, which is the I hat plus Y, which is the J hat. And this should give us two equations. Negative VB will be equal to negative 1.2 plus VCP multiplied by cosine 45 degree. And this is based on this I, and this is the term I, and this is the term I. Let's do the same thing for the J. We have 0 on the left-hand side, but we have 1.2 plus VC with respect to P sine 45. And this is two equations and two unknowns, VB and VCB. And this should give us that VB is equal to negative 2.4 I hat, and this is meter per second, and VC with respect to P is negative 1.7 meter per second. So this is the magnitude. If we want the directions, so VB as a direction, it's a given, sorry, this should be negative 2.4, so negative 2.4 in the I hat direction, like what we did here. So we got the magnitude, and we know it's in this direction based on the omega. And VCB, this is the magnitude. And if we want the direction, we multiply the negative 1.7 by cosine 45 and sine 45, which will give us negative 1.2 in the I hat and negative 1.2 in the J hat direction. So this is for the velocity. So what if we want to solve for the acceleration? How the problem will be changed? So let's figure it out. So if we want to solve for the acceleration, it will be much more difficult. So let's write here part 2. acceleration. So for the acceleration, we will have A at B at A, AB with respect to A, plus AB with respect to B. So let's draw a circle and see how these accelerations are mapped. We have this as point A. Okay. So this is point B is on this arm. So this is an arm, our arm, and we have an omega. And let's assume the alpha. So we have an omega in this direction. Omega AB, 3 radian per second. And let's assume that we have alpha AB is equal to 0. So let's see what is the acceleration at point P. So here's point P on this body, and there's a point B on the circle, which is the black one. So the black one related to the circle, and the blue one is related to the arm. So if we are looking at the acceleration of B with respect to A, it should be, if we have an alpha, it should be something like that. So if I have the alpha AB has a number and it has this direction, so this will be AB with respect to A tangent, different color. Okay, let's assume that we have alpha is in this direction, alpha AB. This is just in case if we have an alpha. So we will have AB with respect to A in the tangent direction, and this will be AB with respect to A in the normal direction. So we got this one, and A is 0 because it's not moving, so the A tangent and normal will be 0. And let's think about AB with respect to P. So let's focus, make a close-up view on this point. So we have a bar here, and this bar has a point P at this location, and it intersects with here is point P. Like, let's assume that there is a separation between them. So the acceleration of B with respect to the other one, it should be related in this direction, like what we did in the velocity here. Something in this direction. So it's either in this direction or either in the other direction. Like, let's assuming that they are going away from each other, like here. Sorry, let's make it blue. And when this body moves like this, point B is still on the circle, but point P is somewhere here. So A, P with respect to B should be something in this direction, or it could be in the other direction. And it's moving on a linear path, so it only have at one component, which is the tangent component, and doesn't have a normal component. Okay, so let's expand this term. We will have A, B tangent, AB normal will be equal A tangent plus A normal, AB with respect to A tangent, plus this will be expanded into 3 terms, AB with respect to B tangent, AB with respect to B normal, plus the Coriolis term, which is the 2 omega B crossed by R, B with respect to B. Okay, let's see what terms that we have is equal to 0. We know that this point is not moving, A, so this two terms will be equal to 0. All right, so what about ABA, AP with respect to A, and we know that the alpha is equal to 0, so alpha multiplied by R will be equal to 0, so this term will be equal to 0 as well. And for these two terms, we know that A and B have a linear, is moving on a linear path, like B is here and the other B is here. So there is no a tangent component. So this component is equal to 0 as well. Okay, so let's continue constructing this equation. So from this point B, we know the direction of the tangent and normal acceleration. Why? Because we know that this body is moving this way, and this will turn out that we should have the acceleration is something like that and something like that. So we'll have AB tangent and AB normal. And this AB normal and AB tangent, so let's put, so we'll have AB tangent. It should be in the negative I hat plus AB normal, and actually we can get the AB normal, it's equal to the velocity at B squared over the radius, and actually we got this, the velocity at B from here. So it's 2.4, this one. It will be equal to 2.4 square over the radius, which is 0.4, and it's in the negative J hat direction. So we needed the velocity to solve the acceleration equation. With this, let's move to this one. This one, we have A here, and we have B here, and we are assuming, not assuming, if we have an acceleration in the tangent will be in this direction. So this is an assumption, but this is the reality of the normal acceleration. So this is AB with respect to AN, and it should be equal to VB with respect to A squared over RB with respect to A, which is this R. And if we want to get this, we can also do this one, or we can have it as negative omega squared multiplied by RB with respect to A. It should give you the same thing. So let's put it as negative omega squared multiplied by, okay, let's have it something like that, omega square of AB multiplied by negative RB with respect to A. This is this term. And this acceleration, we know the direction, but we don't know the magnitude. So we will put AB with respect to B tangent. And I know this angle is 45 degrees. So what we did, cosine 45 in the I hat direction plus sine 45 in the J hat direction. Okay, so this is for this term plus 2 omegas, 2 omega P crossed by RB with respect to B. So RB with respect to B, so this will be equal, oh, this is not R, this should be V. So this should V, let's see what I did write it from before. Oh yeah, so this should be a velocity. Here, VB with respect to B. So let's put it here. VB with respect to B vector. And actually we get this here. So this actually VC with respect to P, which is the same as VB with respect to B. So we got this vector here. All right, so we have our equation here. So let's substitute with numbers. So we'll have AB tangent in the negative I hat direction plus 2.4 square over 0.4 in the negative j hat. This will be equal to omega AB, and the omega AB is given 3 radian per second. It will be 3 squared multiplied by negative RB with respect to A. So it will be 0.4 negative. So let's put the negative outside. And we know that this is 0.4 in the I hat direction, like this. 1R and 1R, and it's 0.4 and 0.4 plus 0.4 in the j hat. And AP, we don't know this term. And we will put the direction cosine 45 in the I hat plus sine 45 in the j hat. And plus 2 omega B, which is the given 3, and it's in the k hat direction, crossed by VB with respect to B. And this is what we got here, negative 1.2 the j hat, negative 1.2, sorry, let's make the I hat first, in the j hat direction. Okay, so the unknowns that we have here is the acceleration at B and the acceleration at B with respect to P. So just two unknowns, and we have two equations, one of them in the x direction and the other in the y direction. And this should be equal to, you will get that AB tangent will be equal to 9 multiplied by negative 0.4 after you sum all the I hat direction, all this I hat, and you do this I hat and another one I hat, and then when you multiply k by j, it will give you something in the I hat direction, and this finally you will end up with negative 0.4 plus AC with respect to P multiplied by cosine 45, and actually this should be negative, and plus 6 multiplied by 1.2, and I think I managed to change the signs, negative 3 squared, and y, in the y direction, you will have negative 2.4 square over 0.4 should be equal to 9 multiplied by 0.4 plus AC with respect to P sine 45 minus 6 multiplied by 1.2. And from this, you have two equations and two unknowns. From this equation, you will get ACB. Actually, this should be B, because we are dealing with this point. We changed the name to B, not C. And this should give you ACB is negative 5.09 meter per second square. And then you substitute in this equation to get the AB tangent. And this should be equal to negative 14.4 meter per second square. And actually, if we want this acceleration in terms of, sorry, we call this P as well. P, and this you will find have AB tangent. This is the AB that we got at this point here. It's in the negative I hat direction. So this is how to solve the acceleration. So the most important thing while you solving this problem is that you construct this equation make sure that you have your sign right in the I hat direction and the J hat. Use all the information that you have to identify the directions of the acceleration and velocities. And also, if you are asked about the acceleration, you should have some velocities because there are some velocity terms embedded in this equation. So you will have to make sure that you will have the necessary omegas and the necessary velocities so you can solve this equation. And finally, while you are solving, keep sure that you are doing your cross product right. When you multiply 3k hat by I hat, I usually draw something like this: I, J, K. If I multiply k by I will give me j, and I by j give me k, and so on and so forth. So yeah, that's all. And I think this is the last topic in this chapter. And the next chapter, we will start it on we will start it on Wednesday, 21st of this month. We will be starting on the force and acceleration of the rigid bodies. So that's all for now, and see you guys on Wednesday.